Hello and welcome to the Explaining Rust Analyzer series of video lectures, where we try to understand how Rust Analyzer works one subsystem at a time. Last time we looked at the crate graph data structure. The crate graph is an internal representation of the project model independent on a particular build system. In Rust Analyzer, we use it to understand what crates we have in a project, what are dependencies between them, and what are their root files. Today, we will continue looking at the base database crate, which defines the crate graph, and we'll actually start looking at the Salsa database, which stores all various bits of input. So, let's get started. So yeah, this is base database crate, and it is one of the most important ones. So what it defines are two traits which are annotated with Salsa procedural macros. So Salsa is really the core underlying engine of Rust Analyzer, which actually implements incremental compilation. This is because of Salsa that we can type something and compute completion in real time without rechecking anything, without rechecking everything we have in our project. So it's a bit hard to explain how Salsa works because it's rather tricky and fancy abstraction. But let me try. So Salsa is based on traits, which are annotated with this specific attribute macros. What this attribute macros does is that it leaves the trait intact, but it also defines an actual struct which implements the crate, which implements the trait. And the implementation is done in such a way that when you call these functions, Salsa actually tracks at runtime which other Salsa functions or Salsa queries we run, and that way it ends up not only computing the answer, but also computing all the intermediate answers and all the dependencies between them. So for example, here we have file text query and we have parse query. And if you look at the implementation of a parse query, you will see that it invokes file text internally. So when we run parse query, Salsa will compute the result of this parse, but it also will compute the intermediate result of the text. And what's more, it will also remember intermediate dependencies between query. It will remember that parsing actually depends on a file text. Then, sometime later, when you ask Salsa to modify any of the inputs, it will be able to tell which of the intermediate results are stale and need to be removed, and which are actually safe to reuse in this new iteration. The special queries in Salsa are marked as input, while typical query, like this one, is implemented as a function which calls other queries. The input queries are inputs. That means that they are set explicitly from the outside. And yeah, in terms of how actual queries look like, the first argument to a query would be a database, and that database would be a struct which implements the specific trait. So when you implement a query, you can actually call all other queries available on this database. If we look here, we see that the amount of inputs of Rust Analyzer is actually really small. And that's one fun thing about this project, is that you start with some basic building blocks, file text and crate graphs, and then you build pretty elaborate thing which does parsing, name resolution, and in the end it finishes in this syntax highlighting which understands semantics and all that fancy stuff. So let's look at the four inputs. First is file text, the actual text of the file, then is source root, which group files into disjoint sets. So we can ask for a specific source root which files it contains, and we also can ask for a specific file which source root it belongs to. This probably would be better modeled in some kind of a relational database, but in Salsa we have to have two symmetric queries here. And finally, you notice that these queries are actually in two different traits. Why is that? So that's a pretty complicated setup. I don't like it, but I think it is required to make the underlying compiler engine more pure. So when we discussed credit roots, I've said that one reason why we need to have a concept of credit root, why we need to know upfront which set of files a crate is comprised of, is that sometimes you have files which are actually unlinked with the query, with any other traits. So if, for example, I have some file.rs here, you see that it doesn't get any syntax highlighting, doesn't get any semantic resolution, and that is because this file isn't actually linked into the crate graph. I need to have a mod declaration here to actually make it work, and there isn't a mod. However, some basic functionality still works. So for example, if I define struct quox here, I actually will be able to get to it via symbol index. Also, minor things, I guess I wonder if, no, even basic type inference doesn't work, but stuff like extend selection works. So I can do things like this. By the way, extend selection, I guess it's called expand. Yes, expand selection in VS Code is one of the best shortcuts. So you start here, and then you select bigger and bigger syntax nodes. So yeah, basic functionality works. And for it, Rustlizer needs to know that this file is a part of a project, despite the fact that there is 0 crates which actually include this file. So, but this is related only to an IDE. In actual compiler, we need to strictly follow RC and to strictly only link files which have mod RS declarations into our crate. And there is so there is like a tension between what an IDE needs to know and what a compiler needs to know. I don't want to give this extra knowledge to the compiler. That's why we actually split the source database into two traits, two different Salsa databases, source database and source database ext. So what source database knows is everything that is available to compiler. Source database ext is everything which is available to an IDE. And because I cannot use trait inheritance in the simple way here, I don't actually remember the details, but basically like you would want to actually make, like you would want to move this file here, for example, because obviously compiler needs to know the file text, but that's doesn't work for some reason, and that's why there is like this file loader indirection. So file loader plus source database is what's available to the compiler, and you note that file loader duplicates some queries of source database ext. And these two queries, these three queries are actually available only to an IDE. What else interesting do we know about the input? One interesting method is this relevant crates. So what this method does, it takes a file ID and identity of a file on a disk or in editor's memory, and returns a set of crates which potentially include this file. Why do we need this? Well, as you recall, Rust Analyzer doesn't have a concept of a current crate. It works with many crates at a time. And every time you invoke any ID functionality, like for example, I can hover over a type and control click on it. What this starts with, it actually starts with a file position, an ID of file and an offset of this file. And from this file position, you need to actually understand what semantic thing is at the current position. The problem here is that you need to understand, like to even start getting semantic analysis of Rust code, you need to understand which crate thus this file might be in, because in theory, because Rust has this like path attribute, which can point like anywhere, like tmp some crate.rs. Because Rust has this kind of things and also like include things, include macro. In theory, any crate can contain this file. So to handle this given only compiler information, we actually need to walk through every crate, fully expand every crate, and understand which file it belongs to. But obviously in IDE, we really would like to avoid doing work which is not strictly necessary. If we have a single file open in an editor, we only want to process these single crates. We don't want to process any other crates you might have in your project. So that's where the relevant crates method comes in. It returns the set of possible crates for a file using only source root information. So it doesn't do any kind of analysis, any kind of macro expansion or module tree building. And it actually is implemented in a rather simple way. We take a file, we ask for a source root, which contains this file, and then we ask for source root crates for this source root. So we go from file ID to source root, and then we just ask every crate which contains this source root. And this implemented is in a rather trivial way. We just iterate every crate we have and check. Okay, yeah. We iterate every crate we have. For every crate, we take its root file, look at the source root file of this of the source root of this root file, and then filter out those source roots which match the current root. So this kind of like this feels slow because you can have many crates, and each time you ask a potential crate for this single file, you actually need to iterate through the whole crate graph, and that seems non-scalable. However, notice that this is inside a Salsa trait. So this is actually cached, and you build this hash set of crates only once per source root per modification. And notice that the only thing this depends on is the crate graph. So after crate graph was updated, you might call this several times to compute for each source root the comprised set of crates, but after that it is cached. And the crate graph actually is a rarely changing thing. The crate graph only changes when you edit cargo toml, add new dependencies, remove dependencies, that sort of stuff, and that is a rare operation. So here Salsa actually effectively makes Rust Analyzer parsed. Okay, so to reiterate, These are salsa traits. They are defined inputs and a couple of derived queries. They are set up in a fancy way, split in two and interacting via this file loader, simply because we want to hide parts of those queries from the compiler, but expose them to an IDE. Now, let's look at how we actually populate those inputs. This happens in the change module. So, change is a representation of a diff between one state of the world and another state of the world. Everything that happens, every typing, every modification of cargo toml, every git switch branch in the command line, eventually manifests itself as a change. And then the change gets applied to the database. And let's take a closer look at how it is done. First, a change might contain source root, a vector of source roots. This only happens for changes which actually add or remove file. So this is a pretty rare operation, because a common operation is just changing the text of a couple of files. So if we, and yes, despite that this is like a change and a diff, the information here isn't actually a diff. It is a current snapshot. So when roots is non-none, it is the current set of roots. We shouldn't like add or remove those. We should just set the current roots to those. So how would we do that? Well, we just iterate every root. And then for every root, we iterate every file and say that the value of file source root query for this file is this root. And then we say that the value of this root is this root. Well, like the last one was confusing. Basically, a lot of things, like not really like a lot of things, like everything in Rust Analyzer is identified with IDs, and ID is just a new type around an integer. So a lot of queries just associate IDs with actual data of the entity which ID refers to. And this happens with source root query. So it takes an ID of the source root and returns the contents of a source root, where the contents is a file set. Okay, so you might notice that I'm like suspiciously not talking about durability. I will do it just after I explain the whole apply method. So after we've dealt with source root, or if there aren't source root modifications, we deal with file changes. So again, we iterate every file and its current text. We figure out the source root, and then we set the file text to the current value. Finally, if a change also contains a crate graph, we set the crate graph. And again, crate graph is optional in change. So if this is set to none, that means that the current crate graph works. If this is set to some, that means that the current crate graph should be thrown away and a new should be installed instead. So let's get back to those durability things. Durability is actually like simple. We look at the source root, and if it is library, durability is high, otherwise it is low. What does it mean? Well, actually, this is one of the coolest optimizations we implemented in Salsa, specifically for IDE use case. So again, coming back to Salsa, what you have during the normal operation is you have a graph of queries, where each query has its current value and a set of dependencies. Salsa also stores a global version, and each query remembers the last version when it was valid. So when you make any modification to the data inside Salsa, you increment this global version. And that means that after the change, every value in Salsa becomes potentially invalid. So let's say you are at version 3, and all the queries are at version 3, and then you modify stuff, and then version becomes version 4, but all the stored data is actually in version 3. And when Salsa executes a new query, it needs to check if the current value still works or if it doesn't. If it still works, it updates the version for the data from 3 to 4. And it needs to do this for every query you actually ask it for. In other words, yes, and the way Salsa actually updates it, it works through dependencies and recursively updates every dependency. That means that, say you have n queries in Salsa, and you do a modification, and then you ask something. That means that Salsa needs to walk through every one of those n queries and mark them as not stale. Even if you don't do the changes, the amount of validation work is actually linear in the size of a database. Well, it is proportional to the to the size of a transitive dependency set of a query you are asking for, but usually queries like usually we're interested in interesting queries who do a lot of subqueries. To say it in a simpler way, if you validate just every query upon every modification, you spend a lot of time, and that's bad. And where are the this is where durabilities are coming from. So every input in Salsa is classified as durable or not durable, and that means, and like the semantics here, the desired semantics, is that durable inputs change rarely, and fragile inputs change frequently. And instead of maintaining a global version, Salsa has a version per durability. And when you make a change, only version for this durability or lower durabilities is updated. Currently, we only use two durabilities, high and low. And that means that when you modify low durability input, only low durability is invalidated. If you modify high durability input, all durabilities are invalidated, so both high and low. And you notice that we mark libraries, so everything from Crates.io and everything in the standard library, as highly durable. That means that normally during invalidation, Salsa doesn't have to revalidate standard library crates. So the amount of revalidation work is proportional only to your code, and that is much smaller. And let maybe actually try to observe this in practice. So I wonder what's the best way to do this. Okay, let's first build Rust Analyzer. And while we are building it, let's where it is raw profile. Yes, let's change the raw profile crate. So yes, this raw profile is a special environmental variable which controls internal Rust Analyzer profiling. So you see that it says that we should log everything which takes longer than 200 milliseconds. And here we get a hierarchical tree of stuff which works slowly. So the build has finished. Also, for some reason, like VS Code build doesn't work. So if you're watching this video and would like to fix some TypeScript code, please look into this. We will discuss and change. Okay, so we've rebuilt the Rust analyzer. Let's reload window and wait until everything is done. Still can't use my keyboard shortcuts. And so let's see what happens if we type here. So you see that basically nothing takes more than 200 milliseconds while we are typing, because there's like very little changes here. Okay, so that means that, yeah, we react to updates in a fast way. Now let's try to actually mark everything as high durability. And let's rebuild Rust Analyzer and see how this affects the overall runtime performance. Okay. Again, the initial loading should take the same amount of time, because durability affects performance only during invalidation. Okay, so now let's clear this. Surprisingly, it is still faster than 200 milliseconds. That's not what I would have expected. Okay. Maybe I'm in an error here, and this isn't actually causing us slowdowns. Yeah, that is the right thing. And okay, yeah. At this point, I'm positively mystified. I wouldn't expect this to like completely grind to a halt and stop working entirely, but I definitely would expect to see much more changes here. Like this, like significant lag, which actually causes stuff to output something in the profile information. Okay, interesting. Yeah, I guess this bears additional investigation. Anyway, in theory, durability should make the stuff significantly faster. In practice, it seems that it is fast enough even without durability, which is mystifying. No, let's actually look closer here. Let's change this to 100 milliseconds and reload. Why am missing the short case? Okay, now stuff consistently takes more than 200 milliseconds. That's strange. Have I failed to actually restart the server last time? Okay, and now no, nothing takes more than 100 milliseconds. Yeah. So what I'm trying to do here is I'm reducing, like increasing the sensitivity of this profiling tool to make sure that we get at least some output every time. So we can see if that changes after our durability change. Okay, we can see that stuff takes about 70-80 milliseconds to complete. And by the way, that's one confusing thing here, is that you see here that a lot of things take approximately 70-60 milliseconds, but that is because they all wait on the same query. So it's not like the total amount of time is the sum of those things, because those things are running in separate threads. We have seen the task pool in one of the previous lectures. So these are waiting times, but waiting happens in parallel. Okay, so we get a baseline of like 70 milliseconds update. And now let's revert back to durability low for non-library code. And let's install Rustalizer. So I'm passing dash server here to only build the Rustalizer binary without building the extension. And I reload window. There is like some kind of like reload Rust analyzer or something like that. Restart maybe, yes, restart server, but I actually never use it. I reload the entirety of the VS Code every time. Maybe that's not the optimal workflow. Okay, yeah, so we see that after we reverted this change, the stuff did get significantly faster. So it was like 70 milliseconds, now it is just 17 milliseconds. And actually you are not seeing most of the things here because they take less than 16 milliseconds, what we set it in array profile. So you can see that this optimization actually works. Okay, so yeah, it works. It's just that even without this optimization, Rust analyzer is like crazy fast. Well, not crazy fast, but fast enough to like not being horribly slow. And this one is interesting. This one is actually something I'm concerned about. So if you recall in the lecture about the main loop, I've said how cool is it that there is a single place where everything happens. So you can print how long it takes and you print the actual event, etc., etc. And I also told that we really, really don't want handle event to block. And this 18 milliseconds spent in handle event is actually pretty bad. Like it shouldn't take 18 milliseconds. It should finish much, much faster. And this is something to look into once we want to push performance of Rust Analyzer to where it really should be. Overall, actually, I must say that I feel that Rust Analyzer isn't really optimized for performance like at all. It allocates all over the place. It uses very inefficient data structures. We did get a big O complexity correct, and that's why completions most of the time don't lag. But I really looking forward to the time where completions are rendered in less than 16 milliseconds. So they're like basically synchronous and you never need to wait for completion at all. Anyway, this was about change struct, which we can apply to the database, which causes us to set inputs. Oh yes, I realized that I didn't explain the obvious to me thing, is that what Salsa macro does is that once you have an input method here, it will automatically generate for you set method name method and also set method name with durability. And that's what we are using here. Okay, so this covers evolution of an actual state stored in the Rust analyzer. Finally, I want to cover some file. I never hit the right key. Finally, one thing I want to tell you about in this base database is the fixture. So one cool thing about this change struct is that it both is very simple, like it's just some data, like 3 fields. And also it can describe everything which can happen to the state of Rust analyzer. You can construct a change which describes pretty much arbitrary Rust projects. And we use this for fixtures. It probably makes sense to show you rather than explain. So let's take a look at some type inference test. Yeah. This would be an interesting one. So you see that we invoke this with many files method, and what it does is that it takes text, parses it into a change fixture, and a change fixture is something which contains like some extra data, and also that change we've just looked at. And then it creates an empty database and applies the change to the database and returns, as we're going to with many files for this one, and returns the database as a result. Now, if we look at how this is actually used, do we have something interesting? Yes, this one. So you'll notice that this is a string literal. So there is like a nice hack I will be talking about sometime later that allows us to actually highlight this string literal as Rust code, but this is just a string. And it is passed into that check impl and then with many files, and then it gets here and gets parsed as a fixture. And what this string contains is a special DSL, which basically describes a change. Or rather, not even a change, but like the final state of a Rust project. So for example, here we have a project with 2 crates. The first crate is up to this point, and the second crate is up to this point. This /dash prefix indicates meta information about the fixture. This thing identifies the file name, this identifies the crate name, and this identifies the dependencies between the crates. Actually, let's just print this. You'll notice that I've used the PPD snippet, which is built in Rust Analyzer, and it basically allows you to do this. I know that there is a DBG thing as well, but I just find using manual println more convenient most of the time. I only used DBG snippet when I need to print some intermediate value, like if I want to do this, instead of introducing some extra variable. But here, I don't have an expression, I just print this. Anyway, just like small debugging kit. So let's just run this and see what the output looks like. Also, we've been editing base database, and base database is a dependency of a whole lot of crates. So I expect that as this is the first time we are recompiling in debug, this will need some recompiling. Okay, so we don't have, obviously, because we actually are interested in this one. Again, notice that I am using Rust Analyzer run workflow here because it's really convenient. I modify the code and I rerun the last test. So yes, let's look. Let's actually close this. Let's look what this crate corresponds to in terms of change of crate graph. First, there is a single source root with two files, and we have two files here. The source root isn't a library. Then we see two changed files, and yes, one problem with Rust Analyzer is if you print stuff, it gets verbose, like changes, like it's a simple struct, but it can be very big. So that's why in debug we have this concise representation. I probably should use like if Fimity alternate here or something like that. Actually, yes, we are curious in the verbose representation, so let's just derive it. Again, you see, like rerunning the last test is like killer feature for productivity. If only Rust compile times were better, that would help even more, but oh well. Okay, yeah, now we see the whole deal. Okay, and we see that two files, obviously they have IDs 0 and 1, and the state of the first file is now this. So this is this one. Interesting that they go in the opposite direction. And the state of the file, first file, is this one. And we have a crate graph. So crate graph has two crates. So like it's like horrible syntax. Like Rust derive debug is awesome, but not always. So this is one crate, and this is another crate. The first crate has file ID 0 as a root. So this crate 0 is actually this one. And that doesn't make sense. That doesn't make sense. Yes, because I get confused by I128. Obviously, the second file is like the second file, and the first file is the first file. Okay, so this first crate has first file, this one, as a root, and it has the second crate as a dependency. And the second crate is known under the name other crate. And here is this other crate, which itself doesn't have any dependencies, but has the different file as a root. And that's it. And of course, you can use this change to describe arbitrary complex projects. So just for fun, let's actually try to print. Yeah, let's just print every change. And let's look how. Let's do even better. Let's say std fs right. And where shall we write it? Let's write it into /home. Change the bugum. Okay, but actually, let's do some command line shading to make sure that we didn't make a typo here. Rebuild it once more. Yeah, like incremental rebuilds of Rust Analyzer are actually not super bad. And reload. And by the way, we now see these notifications about overly long event loops, which I've talked about previously. And now we should have, yes, we should have changed dbg. And yeah, as you see, this is like big file, some like numbers. Actually, I have no idea what those numbers actually signify. Okay. So that isn't actually like the analysis change for the whole file. It is just the analysis change for a file from some crate, and it feels like something from libcore or something like that, where we have like a giant lookup table. Yeah, so it's yes, so it's like modification to a single file. So I said that I hope to show like a real crate graph, but anyway, so you now know that you can just like print the stuff and understand what is the data that Rust Analyzer works with. And again, something which I repeat time and again, that the code doesn't matter. What really matters is data, and this base database is the central point, which collects all the data Rust Analyzer works with in this two source database and source database X traits, and also encapsulates the way the state evolves over time using this change method. Okay, finally, it took us 2 tries, but we've covered this crate, and next time we will be talking about, yeah, actually I don't know what we will be talking about next time, but probably now that we fully understand the big picture, the entry point and the overall evolution of the state and the main loop, it makes time to switch from the top-down view to the bottom-up view and talk about lexing and parsing and syntax trees and all that stuff. Anyway, I might change my mind. You will know this next time, and I will probably know this next time as well. Okay, thank you for listening. Bye.